Okay, so welcome to the second part. So we still have to find the operator. And we started with a star operator, now we have a plus. The question is, what do we want to add? And what does it mean? What's a hard thing? Because at this moment, everything is easy. Okay. Now, what we do is we want to have scalar multiplications. And we are, first of all, we're not working in real numbers at all. You can imagine why we won't work in real numbers, because we get the problem of position at some point. So that's the first thing. So if you do all these formulas, you lose a little bit precision in every formula. So doing cryptography in R is maybe not desirable. The next thing is, so we could work in residual fields modulo P, or we could use a Golar field with 2 to the L. Warning, so the formulas that we have shown work here, but they don't work here. And I can show you why this doesn't work. It does not work because we are dividing by 2 at this point here. It's something we cannot do in the residual fields. So for residual field, we have to do a different Golar. We have to use a different elliptic curve. Basically, we use an elliptic curve of the structure not minus px, but we have minus px squared. So it's still an elliptic curve, but we have to shift it slightly so we don't have to divide by 2, which is something you is not quite easy here in this field. Okay, so the next thing, so we have a plus operator. We also have a minus operator because we have an inverse element. With that, we do the following. What we do is we say if we have an element and k times added to itself, we get a multiplication. K will be a natural number. So it's the number. So we take the same element and say q plus q plus q plus q plus 1. So we already know what q plus q is, because for q plus q, you have q and q, and you basically compute the intersection here from q plus q and map it back. So that's q plus q is clear. But q plus q plus q is already somewhere else, and you somehow get around. So we'll do, I think next week we do an exercise where we look in how this really works out for residual fields. Now you could do this like that, q plus blue and so on, but you could do it more efficient by using iterative squaring. So you can compute the powers of 2, because now this factor is a natural number. So you have 2 to the I is 2 to the I minus 1 times q plus 2 to the I minus 1 times q. And so with 1 plus operation, you get the next power of 2. And this way you get an efficient way to do scalar multiplication, which is in the logarithm of k times additions that you have to perform, which you need because this will be k will be a large number. So what is the complicated thing? The complicated thing is that if you give him p and q, it's hard to tell you which k produces the p. If the p is equals k times q, for non-trivial q and large k, computing k is hard. So that is the elliptic curve discrete logarithm assumption, which is confusing because there is no logarithm. There is no logarithm because we want to have this discrete logarithm assumption like the discrete logarithmic assumption for residual fields. So we just copied the name, but it's not a logarithm. You can rephrase this operation as exponentiation somehow if you call the addition a multiplication, but it's still not a multiplication, it's still not a discrete logarithm. Okay, to make things easier, Now the thing is that you share later on, like in LGML, you share the same field with the other. So this field is not secret. So the field will be the parameters of the elliptic curve and the starting point Q, which is something like a generator. If you choose this carefully, these parameters, and maybe also the prime number modulo to that everything has been done, then you can find an n such that 1 plus n times q is q. And after that, it will repeat, because this is just an addition. So 2 plus n times q will be q plus q, and so on. If you have that, you can also do things like, if you have q times k, that you could have compute something like the inverse. So if you have L times k times q, you get q again, something you have to do. This is something we do not need for the elliptic curve cryptography on the next slide. It's just a nice property. If you have that, and then the next thing is you choose this n to be a multiplicity of a large prime factor. So because now we have something like, again, a group, a ring, and if this has a large prime factor, then you basically have the same thing as in LGML. And this is what they do. So they so usually you do not choose these elliptic curve parameters unless, in LGML you can choose it safely if you have a strong prime number. But here don't choose it. You just pick it from a set of values which are common. And then you also get these kind of parameters where the elliptic curve repeats. Okay. But after that, it behaves the same way as discrete logarithm, but the only difference is that multiplication here is called addition. And what is in the exponentiation in the other field is here a multiplication. And so we can get a cyclic subgroup. Okay, so that's now it closes. And from you, if you look at this of a computer scientist case, you can forget everything about these formulas before, because that will be done by some library. The important thing is that you know what it does and how it can be used and how it can be interchanged with something else and what is the assumption, what is secure and what is not. Because if you don't know, maybe you give out some kind of secret. Okay, now let's do LGML encryption again. The cool thing about LGML encryption is that although I presented it at the beginning of this lecture, you probably have safely forgotten how it works. Who remembers it? Okay, it works. Wonderful. It's like I erased your memory. So what we have is we have in LGML we have a secret key which is called X. Yeah. And we have a prime number P. Prime number P. And we have a generator G. So you have something similar. You have this extension field, you have this N, and you have a starting point Q. The Q is basically the G, and the secret key X is here called S. For public key is calculated as Y is equal to G to the X modulo P. Here what we do is we have a public key, which is the secret key multiplied by Q. Now, if you think that addition is something like multiplication, then it's the same operation, but it's not, we know. But basically, we are getting one level down here, so S times Q. Now, for encryption, in LGML, how did we do encryption? So we had a random number R, and we produced two messages. And here we have a random number K, and we also produce two messages. The first message will be the random number times Q. And in LGML, the first message was secret. No, it was G to the R. Okay, that was the first part. You can see that's the same thing somehow. And the second part was in El-Jamal, the message. If I would torture you, would you get the correct answer or just no? Okay. At least you're safe from the Secret Service now. And the public key to the power of R. That's the second part. Modulo B. Maybe it's good for you if you don't vote for closed book exam at this point, you know. It's maybe you should vote for at least one page. So if you don't want to learn that and have in your brains and so on. So okay. And you can vote 2 weeks for that. I don't know whether I respect it or not, but I will definitely publish results and will live with the consequences of ignoring the result, as I learned from our chancellor. Okay, so enough politics. So what we do here, we have M, the message. The message is somehow a point on the curve, whatever that means. And now we have plus K times P. So we have K times P, which is again the same thing we are doing here, but just for exponentiation. So if you use it as a sub-function, you have doing the same thing, because you have this one operation which is secure, which is g to the x, which is exponentiation, and here you're using it with that. Now for this we have to put the message on the curve. How can we put the message on the curve? Any ideas? Okay. For this, we go back to our visualization. Okay, this is the curve. I just zoom out. This curve is okay. The problem is if you just take the message and have an x and y coordinate, probably you're here somewhere. So the chances to hit that curve are very slim. But you could do the following. You could start with a y coordinate, and when you get an x coordinate by solving that, or you could start with an x coordinate and compute the y coordinate, but then you have to make sure that you are on the correct side and you have a defined value here. So that's the problem you have to care, and because you have to get result again. So that's a lot of methods to put this. This is not part of the presentation here. Different ways to put messages on the curve, but this is a small problem you have to somehow solve. Okay, let's look at decryption. How we decrypt in El-Jamal. In El-Jamal, we take the second part, which is C2, and divide it by the first part to the power of the secret key. And that gives the message. In elliptic curve, we take the second message. We subtract S times the first message. Yeah. So division is subtraction and exponentiation is multiplication. So it's the same thing. Okay, yeah. Yep.
For one value of x, you could have 2 values of y.
Yeah. And it's also the same problem for y. You could have several values. And this is the problem we already have seen when we had looked at Robbins encryption, because Robbins encryption, we could have several roots. And so we need some padding. And so this gets technical at this point. So that is basically the problem, that there's not a unique way to get onto this curve. So unless you do something. And you have to do this, but this is something we do not do in this lecture at this point, and because we want to do more exciting things. And the next exciting thing we will do is, it's also a very basic feature. So we are now leaving this. We will come back to elliptic curves, and we will also come back to El-Jamal. because each of its asymmetric crypto systems has a digital signature. And because you could work in order to encrypt it, but you can also use it to build signatures. And so I now start with digital signatures, which is a very important application of asymmetric cryptography. So what we need compared to asymmetric cryptography, we have something completely different here. But we still can reuse a lot of things. So first of all, we need keys. Digital signatures have a public and a secret key. Then we need a signing algorithm. The signing algorithm is something that the person does who's producing the digital signature. So here we use a secret key. So we start using the secret key and produce a signature sigma. And then on the other side, we have verification. Now, while for public key cryptography, everybody can send me a message, I'm the only one who can decrypt it. For digital signatures, I produce a signature and everybody can verify it's okay. That's the idea. So for this, the public key is used and everybody can verify that I'm the only one who can do that. So it returns true if a message produced by the signer and otherwise it's false. Which has a lot of problems somehow, because it means that somehow if I sign this document, I cannot take the signatures back somehow. It's out there and I have to live with that. And you can put a date on it and say, this is valid from here to there, but the signature is out there and everybody can verify it. The security is the ability to withstand forgery, that somebody else makes the signature. And just imagine how do we solve this in practice? So in history, usually you have kind of ring and then you put it into wax and you put it on your document and you have your own ring. And if you look some of these, what's called these movies about the Vatican and secrets and what's it called? This was some fashion 10 years ago. And then first thing, Illuminati and so on. The first thing it's a seal ring is broken by the Pope and the Pope dies, even before they carry him out of his chamber. So and things like that. So that was really proof and secure. Nowadays we are using our handwritten signature, which is totally safe. Nobody can falsify that unless somebody invents a machine who can copy paper into other paper. Or maybe a machine which makes photographs, and that would actually break the scheme, and nobody will use it again. So, yeah, but that's crazy talk, I think. Okay. Otherwise, we would have to use digital signature in practice, and everybody would use it, which is not the case, obviously. Who's using digital signatures? Not that probably. Maybe it's built in your browser and browser is using them for something important, but not you when you correspond to your bank about money. Then it's okay, handwriting. Okay. So now the idea is there is a general model how to do this, and it works with trapdoors. And a trapdoor is that you can do one calculation easy, and for the other one you need some kind of secret information. And this is usually a public key crypto system where you have a key generator, you have an encrypt function, and you have a decrypt function. Now the idea is the following: you switch E and D. So instead of you decrypt the message in order to get the signature, and the other one can encrypt it. So because encryption is done with public key and decryption with the secret key. So in this idea is the following: you use the same key generator as a public key cryptography, like RSA, P times Q, and maybe E and D, such that E times D is 1 modulo the Euler phi function. And then you have a signing function, and for the signing function, you decrypt the message and get nonsense. because the message is not encrypted. And when you send the message and the nonsense, then everybody can see by encrypting the nonsense that you get the message. So that's the key thing. It looks like a good idea. But there are some problems. So the problem is that you decipher something, and if you decipher something, when the decrypted code is in the hand of a public, you can sign something for somebody else. Yeah. So give me the signature and say, okay, I can sign this. This doesn't make sense. And so that means never use the same keys for signing encryption. So you need 2 new keys. So either you do signatures with that or you do encryption. Otherwise, you have potential that somebody is doing some forgery. Another problem that you have are replay attacks. So if you have a message like send Bob 10 euro, yeah, then Bob might reuse that very often. Yeah, so because it's good for Bob, obviously, to get 10 euros, and that's something, yeah, take this again. And in CryptoCoin, this is called double spending problem, that you spend money twice. So you have to some kind of mechanisms to make sure that this doesn't happen. So some context. Now the solutions are, first of all, at this stage, we didn't use cryptographic hash functions, but you should use it always. Never sign an unhashed message. Hash the message and then sign it. So that's the first thing. And the next thing is we have to add nonces, which are random bits used only once to the message. You have to actually randomize the message somehow at some insignificant part, and then you hash it, and then you do the signature. This already solves a lot of these problems that we have here at this point. So if you look at the attacks on cryptographic schemes, we have the same thing as for public key attacks. You could just attack it with a key. So you know the public key and you want to calculate the secret key. You could attack it with the signatures that you know. So the adversary knows, of course, the public key, and then you get some kind of pairs, and you want to forge new messages, which could be problematic. For example, if you use public key cryptography, which is homomorphic. So when you can multiply 2 messages and get the product of 2 signatures. So this is problematic in this case already. Or you can choose message in such a way that the signer signs your message and you gives out some information to it. Okay, what is the result? The result is a digital signature forgery. And so there are different levels of forgeries. And so we want to create a pair of messages and signatures which are valid. And the first type is a total break. So basically, you compute the secret key and everything is lost. Slightly less bad, but still very, very bad, is universal forgery. You can actually sign everything you want. We don't have a secret key, but you can do that. Maybe you have selective forgery. So you have given a message and you want to attack this message. You want to produce a signature, and now you do some kind of chosen message attack in order to get this. So you do some interaction with a signer, and then you basically can produce this message. Maybe it's restricted to some mathematical properties. So maybe you cannot forge every message, but only some of them. And the weakest one is existential forgery. There's at least one message signature pair that can be created. You don't have any control, but you can produce some of them. So why is this helpful? Maybe you can show, I can produce signatures, I must be him. But maybe it's enough. I can sign this thing, you see? So I must be this person, so you trust me. So that is a problem. And this is something which happens in RSA. So we plug it in for some example. So most interesting, all these slides that I produced here is something which is not in the book of Delfs and Knebel. So I had to look into the lecture notes of Goldwasser and Belair to get a general definition of what digital signature is for the book of Delfs and Knebel, which is underlying most of the things in this lecture. This was too basic to put into a book. So they just forgot it, maybe. I don't know. Or maybe I overlooked it. So I didn't find it. Okay. But this is in the book again. So that's where the book starts. The basic scheme uses RSA. So RSA, you remember, we have a secret key, which are two prime numbers. And we have, as a secret key, also some number from which is co-prime with P and Q. And the public key is the product and the inverse modulo phi of n, which is the same as P minus 1 times Q minus 1. Okay, so that's all known. The signing is that you have a message and you come sigma, and that's the first mistake I'm doing here, because this should be D. We decrypt the message. So we compute m to the d modulo n, and then we send this information. And for verification is we compute sigma to the e, and then sigma to the e is sigma to the e is the message to the d to the power of e, which is m to the d times e modulo phi of n, and this is modulo n. And we made this to be 1, and so we get the message back. And if the message was smaller than n, then this is unique, and basically it says that this should work. So if Alice signs the key, then Bob will accept it. But Bob will also accept signature which are not produced by Alice. If Alice has access to the key. So what would you do? You start with a signature. So you could start with sigma prime. And that's your message now. I'm a message now, so that's a signature. And then you produce a signature, which is the encrypted signature. So now the message is the signature to the power of e. Yeah. What does it mean? Probably nothing. Probably it's just a bunch of bits which have no meaning at all. But I can produce a pair of message and signature with a message which is just some kind of random number. Okay, so that means RSA can be always existentially forged if you use it like that. Okay, so that's a huge problem here for RSA. And that's something we have to resolve at some point. And we continue with that in next week when we try to resolve this problem. Of course, padding will play a role. We will use cryptographic hash functions, and we will also revisit El-Jamal, and we will revisit elliptic curve cryptography and show how we can do digital signatures with them. But that's it for today. Thank you for attention, and see you on Thursday in the exercise. I hope that you have all done your exercises, so otherwise I have to do it again. Thank you for attention.